Oh, thank you, Chairperson. I'm Motohiro Oshima from Toyama Prefecture University in Japan. So today, to talk about customization of OpenFOAM Lagrangian solver for superheat spray evaporation. Oh, thank you. The subtitle is here. So I talk about the comparison with OpenFOAM numerical result and the Kiva. I don't talk about the numerical result and the experimental data, so because I don't have more time to discuss this. Characteristics of flashing spray is wider spray shape and shorter spray penetration, smaller SMD. So this figure is an inner spray structure and various superheat conditions. So PA is ambient pressure, PS is saturated pressure. As you can see, the as you can see, the superheat conditions are the spray spread wider and shorter spray penetration and a smaller SMD. This figure is a phenomena inside the flashing spray droplet. This phenomenon is very complex. The bubble inside the droplet is a nuclei and grows and collapses. In OpenFOAM, flash spray cannot be simulated correctly. However, a user can set the flash boring model in the spray cloud properties file inside the constant directory. So names evaporation, a liquid evaporation boil is flashing spray model. In other spray simulation software, the Kiva is not included. CDAJ is included, the flashing model. So this slide is presented in a 18th OpenFOAM workshop. So we contracted a novel Lagrangian solver for superheated spray by customizing the super spray form. This movie is a superheated spray shape at the vertical cross section. And however, the detail of the flashing model doesn't composed in the solver, such as the seat flashing and the Stefan flow modification completely. In this presentation, we have tried to compose the flashing model to this solver completely, and the numerical simulation result is to compare with Kiva and at various superheat degrees. This slide is a schematic image of flashing boiling spray from Swirl Atomizer. So this flash boiling model is proposed by the Professor Rutland group. This figure is a pressure swirl atomizer nozzle. So the injected the liquid, it forms liquid seed, and atomized and form droplets. And the seed flash boiling is calculated by the transient convection limit TCL model, and the seed breakup is calculated by the linear stability analysis LISA model. And the vaporization and the heat transfer at flash boiling is also calculated. The bottom figure is the Kiva result calculated by the Rutland group. So delta T is the difference is of a difference between ambient pressure and the fuel temperature. So high delta T high delta T, so spray is spread and the spray penetration is shorter. Next slide. From next slide, I'll talk about the every model. This figure, this slide is a teacher model, and in this model, half of film thickness near breakup point on seat flash boring calculated by using this equation. H0 is a film thickness at a certain point, and MBU dot is total seat flash evaporation rate from nozzle outlet of seat breakup point. MIJ dot is injection mass rate. Next, this slide is a schematic model of laser model. In this model, the velocity liquid film is calculated by using this equation. So Kv is a constant determined by the injector design and the injection pressure and ambient pressure. And a droplet diameter after sheet breakup are calculated by this equation. And the droplet diameter after flushing atomization calculated by this equation by using droplet diameter after sheet breakup, this one. And in flushing flash boring spray, a spray cone angle is wider. So spray cone angle is calculated by this equation by using the normal spray cone angle and the superheat degree parameter key. Next, superheat drop flash by vaporization and the heat transfer process is this figure shows. Heat transfer vaporization rate is calculated by this equation, and GF is drop flash vaporization rate, and in this equation, Nusselt number is a Stefan flow modification model as the normal Nusselt number by using this equation. Heat transfer coefficient is calculated by these equations. Next, this slide is computational domains and numerical conditions. The diameter of this is a cylinder shape. The diameter is 200 millimeter and the height is 200 millimeter. The injection point is 195 millimeter from the bottom. So the mesh shape is like this. Isoctane is injected to the atmospheric pressure, and the ambient temperature is 300 Kelvin, and the fuel temperature is set 4%. The superheat degrees is 0, 30, 45, 6 Kelvin. Total injection mass is 43.7 milligram. Injection duration is 3.86 milliseconds. Nozzle diameter is 560 micrometer. Initial droplet diameter is 124 micrometer. The cone angle is defined by this figure. The outer is 22.5 degree, and the inner is 18 degrees. Okay, let's move to the discussion. The spray, this movie is spray shape at the vertical cross section. So 395 Kelvin is non flash boiling, and the bottom image is Kiba result. And from this movies, the spray shape, but spray diameter, dropped diameter is smaller, and the spray cone is wider than increasing the fuel temperature. So compared to this result, spray shape is similar as Kiba the result. And this slide is spray penetration, and compared with Kiba. OpenFOAM result is almost same to Kiba until 1.5 millisecond, and the OpenFOAM result is lower than the Kiba result from 1.5 to 3.8 millisecond in 3 cases. So several differences cause that the reason is why is that the several differences of two codes causes penetration differences in non-flash boiling condition is reported by the this paper. In 435 OpenFOAM result higher than the Kiba result because the droplet is appearing in the spray axis from the previous slide. Spray cone, this slide is spray cone angle and the average SMD after breakup. So red mark is Kiba and black mark is OpenFOAM. And the initial spray cone angle is defined at 0.1 millisecond and 5 millimeter from the nozzle in OpenFOAM case. From this figure, the average SMD after breakup is decreases by increasing fuel temperature, and the initial spray cone angle is increases by increasing fuel temperature. And from these figures, this result, spray cone angle as the average SMD at the breakup is almost the same. Okay, concluding my presentation, spray shape OpenFOAM is almost same the Kiba. The spray penetration is at this 3 temperature case. So OpenFOAM almost same to Kiba until 1.5 millisecond. OpenFOAM from 1.5 to 3.8 millisecond, OpenFOAM is lower than the Kiba result. Temperature is 435 case. OpenFOAM result is higher than the Kiba result. Spray cone angle, the average SMD after breakup is almost the same. Thank you very much. Someone knows, this is my question. Someone knows Lagrangian solvers spray well? If you know the information about that, please contact me. Thank you very much.